In this video, we'll discuss how do we decide a function is increasing or decreasing, or whether you have a local maximum or local minimum using the algebraic property of the function and its derivatives, first and second derivatives. So let's recall that the foundation of all the discussion is basically the mean value theorem. So mean value theorem is the foundation of all the discussion we have in the whole section, mean value theorem, right? Mean value theorem. So let's recall that a bit, then we'll see the application, making the connection between the positive or negative sign of first derivative and with the increasing, decreasing of the function y equal to f of x, right? For sure, our assumption here is first f of x, let's say just use f, right? F is our function. F is continuous on the interval a, b, closed interval. And second, f is, like, suppose, right? This is our assumption. Suppose f is differentiable on the open interval from a to b, right? Not including a and b. So our conclusion here is then there is a C inside AB, such that good thing happens. We can making a connection between the secant line slope f of b minus f of a over b minus a. So this is equal to f prime of c, right? So this is a mean value theorem. This is one of the foundation result in calculus. So some very important application. One is increasing, decreasing test. Increasing, decreasing test. Decreasing test. By making the connection between the derivative and whether the function is increasing or decreasing on the corresponding interval. So, and the first result here says if what f prime of x is greater than 0 on an interval, right? Whatever the interval here is, then what happens is f is increasing on the interval, and of course, right, very similarly, right? If f the derivative is less than 0 on an interval, then the function is decreasing, right? F is decreasing on the corresponding interval. That's very nice, right? You can decide a function is increasing or decreasing on the interval, right? So what happens when f prime of x is 0, right? We know that if f prime of 0, then you get a critical number, right? Or f prime of that number doesn't exist, right? So see here, let's decide what happens on the critical number, right? So let C here be a critical number, number of f. So I dot E either f prime of C equal to 0, right? We know what happens when the when the derivative is not zero, which either positive or negative. We want to see what happens when the derivative is zero or the derivative doesn't exist, right? And or f prime of c does not exist. So C here, by our assumption, C here is in the domain of F. If C is not in the domain, then we don't discuss. This is not a critical number. So that's our being a critical number. The number has to be in the domain of such a function, right? So we want to see how do we decide f of c is maximum or minimum or local maximum or local minimum, right? So this is our first derivative test. First derivative test. Assumption is you are given a critical number and you want to decide f of this number is either local maximum or local minimum, right? Very natural result due to this very intuitive observation, right? So you are given a function like this. I can see that, look at, this is our critical number 1, the second critical number here, right? So you can see that if the function is increasing on the left side and decreasing on the right side, then this is a local maximum value, right? And decreasing on the left side, then increasing on the right side, this is a local minimum value, right? These two numbers are critical numbers, which means you have horizontal tangent line, or the derivative doesn't exist, right? And the function here increasing means f prime is greater than 0, f prime is less than 0, f prime is greater than 0, right? So this is our first derivative test, which means you can decide whether f of c is a local maximum value or local minimum value by looking at whether the function is increasing on the left side and decreasing on the right side, or the other way, right? Or sometimes both increasing, then you don't have a local maximum or local minimum value. So that something could happen. Sometimes that could happen. So first result here is if f prime here changes from positive to negative at c, because f of c will be 0 or undefined, then what happens is then f has a local maximum value at c, right? So first example here, and b here is if f prime changes from negative to positive at c. What happens on the right side here, right? Left side, the function getting small, function value is getting smaller and smaller. On the right side, function value is getting bigger and bigger, right? Which means our function is derivative is negative on the left side and is positive on the right side of c, right? And then f has local minimum value at c, right? If the sign doesn't change, on left side positive, right side positive, left side negative, right side negative, then you don't have a local extreme value. Let's see a Let's see a quick example here. We have a function, example. We have a function which is f of x equal to what? Equal to 4x cubed plus 3x squared minus 6x plus 1. So that's a polynomial function, right? We can sketch it. We want to sketch it by discussing the positive and negative sign of first and second derivative. Let's try to decide what's the decreasing intervals and also the local extreme values, right? So find increasing and decreasing, if there are any, right? Sometimes the function is always increasing, that then you get all the increasing intervals. On this interval, the function is increasing or decreasing, right? And local extreme, which means local maximum, local minimum values of f, right? How do we do that? We want to decide first what's the critical number, because that's where the derivative equal to 0. Then critical number divide your domain into a few subintervals, right? And then you'd want to decide on each interval the derivative is positive or positive or negative. You get increasing, decreasing intervals, and in the same time you can decide at the critical number the function either reach a local maximum value or local minimum value or neither, right? And so we can see that before we understand the function, for sure we need to know what's the domain of this function, right? Domain, we knew domain of this function because that's a polynomial. This is continuous everywhere. So this is from negative infinity to positive infinity, right? Another notation for this is all real numbers, right? So let's try to decide the critical numbers first. So f prime of x equal to 12 x squared minus 6x, no, plus 6x minus 6, right? So this is, right, if you want to decide when this derivative, so for sure this derivative always exists, right? You want to decide when the derivative equal to 0. A good way to do that is try to factor that, 6, 2x squared plus x minus 1, right? And so this is same as 6, 2x minus 1, x plus 1, right? So f prime of x equal to 0, you have two solutions, either x equal to 1/2, right? The first factor is 0, or x is -1, right? So these two are critical numbers. So these two are critical numbers. We want to for sure decide this critical number, you have a local maximum or local minimum, right? And to do that, you want to decide besides, right, this point, whether the function is increasing or decreasing, right? Domain is all real numbers. You have two separations, which means you have three subintervals. One is from negative infinity to -1. And the other one is from -1 to 1/2. And the last one is from 1/2 to positive infinity, right? So you get three intervals. You can try to sketch a line, number line here. Left side is -1, right side is 1/2, right? You want to know f prime is positive or negative. Positive means our function is increasing, and negative means our function is decreasing, right? So when x is less than -1, right? Then 2x minus 1 for sure is less than 0. X plus 1 is also less than 0, right? And so which means both factors are positive, which means f prime here is positive, right? From negative infinity to negative 1, f prime is positive, which means f here is increasing. And from when x is greater than negative 1, less than 1/2, right? Then x plus 1 will be positive, right? And 2x minus 1 still negative. So 1 positive, 1 negative. So f prime is negative, then f is decreasing. And from 1/2 to infinity, both factor, you can check that when x is greater than 1/2, then 2x minus 1 is greater than 0. X plus 1 is greater than 0. So both factors are positive. So the derivative is positive. So f prime is positive in this case. So this f is increasing. The function has two increasing intervals and one decreasing intervals. So on the left side of negative 1, the function is increasing. Right side of negative 1 function is decreasing, which means f of negative 1 is a local maximum, right? So by the first derivative test, f of negative 1 local maximum value, right? And similarly, f of 1/2 is a local minimum value. So that's how do we decide the increasing, decreasing intervals and also local extreme values of a function using the first derivative, right? You can differentiate that function and also get quick numbers, always starting from identify quick numbers. And before that, for sure, you need to know the domain. Identify quick numbers, then divide using quick numbers, divide your domain into subintervals, and then decide on each subinterval the derivative is positive or negative, right? Then you know the increasing, decreasing intervals. In the same time, you get local maximum values and local minimum values if there is any.